What is up, you guys? Welcome back to this week's Differential Geometry stream. Last stream was a pretty substantial section from Chapter 2, which each one of these sections is pretty much a chapter in its own, even though they're only, on average, they've been like 2 to 3 pages up to the last section, which was section 19, and the last one was about 5 pages. So to kind of put it in perspective, it was a little bit heavier. This week, section 20 is another 5 to 6 page long section out of this chapter. So between section 19 and section 20, these are the most substantial sections in this chapter, because after section 20, which is what I'm going to read today, they get back to being smaller, and then we finish off chapter 2 and get into chapter 3. But of course, these videos would be incomplete if I didn't rant about something almost completely unrelated to differential geometry, but this is related to differential geometry, which is what my thoughts are actually on quantum gravity. Because a lot of the criticisms of theoretical physics and academia in general right now, like in modern times, in my perspective, are very true. Those criticisms being, like, let's say that you're a grad student and you actually get into a physics program, and well, what got you into that? You had some passion for learning, passion for specifically physics. You hear about, when you're in high school, undergraduate, you hear about innovations, technology, etc., at the cutting edge of civilization right now, and you connect 2 and 2 together and you think, wow, the most advanced stuff out there, it involves theoretical physics. But then when you actually get to grad school and you have an advisor, you're working under some professor, you're not going to go after those, like, I forgot what DARPA, the Defense Advanced Research Project Association, the whole Pentagon of the US, what they call their research. But you have this dream that, just by getting into whatever physics grad school program, you're gonna be well on your way to working on that very utmost cutting edge type of science that doesn't have an immediate application in technology or something, but it's like, we recognize that somebody has to be going for these things. Whatever we means and whatever those things are, it's ultimately innovating at the edge of theoretical physics. But, what does that actually mean when the rubber hits the road, so to speak? Well, the most innovation in our understanding of nature and how do we systemize the phenomena that we observe in nature. On the gravity side of things, the most innovation was due to Einstein, and what that is general relativity, which for me as a non-physics background person, as a math background person, what that means is general relativity is a geometric theory of gravity. But that is one scale or regime of physics, as it were, that the other cutting edge of physics is at the regime of the very small, and that involves quantum mechanics. So you'll often drop in things like, Schrodinger's equation, and you start talking about like the standard model of particle theory, and you talk about the results of the Large Hadron Collider, and where are all these exotic particles that we're supposed to expect according to the theoretical physics estimations, calculations, etc. And the big, more than $1 million question in theoretical physics is, how do you reconcile those two things, the general relativity results and the quantum mechanical results? You could keep going further into this with, say, a historical perspective. There was a time where, what gravity was not well understood. There was not a coherent conceptual framework box for gravity. And so people, scientists, mathematicians, whatever you want to call them, would just toss around terms and force, impetus, momentum, and it's all kind of like this mushy soup that's all molded together. And then gradually over time, these things became more and more distinct, more and more clarified. And quantum gravity could be just like a phrase for stating where the problems are that we haven't ironed out, these kind of differences that are just, that's kind of what humans have been just doing in general throughout the history of science, right? Is we look outside and we see, you could throw a rock and we say, man, I wish I could really figure out how to best describe throwing this rock. It's probably because you want to hit some animal or kill some dude with that rock, right? And instead of it being rocks, eventually you develop missiles and stuff like that. But what is all going on? Ballistic trajectories, right? And so Newton, with his understanding of gravity, we got ballistic trajectories all taken care of. If you're doing anything, roughly in the scale of like what we call everyday life, Newton's understanding of gravity is good for like 99.99% of those things, right? Then you have telescopes and you look out into the universe and stuff like that, and you see the motions of celestial bodies. And it's not about the Earth being round, and I'm not going to go into Earth is flat stuff because that isn't even worth thinking about really. But at some point people were looking out, people like Copernicus and Ptolemy were looking out with their telescopes, and they're like, man, we've got to figure out a way to track these orbits, right? And it was the mathematical frameworks that Copernicus came up with that best fit the data that they had. Those are the kinds of things that advance our understanding of gravity, right? So what did Einstein do to go even further than, it's like if Newton and all that, Copernicus, it all fits together. Why do you need to go even further than that? Well, turns out that, these small like vibrations of the Earth and stuff and of other planets and stuff, those are really important if you want to get more precision on your astronomical observations, let's say, or if you're doing things at an atomic scale, having a rigorous mathematical framework that you can sort of turn the dial on to get to, greater levels of precision. You can build stuff like nuclear weapons, okay? But one of the key things that vindicated Einstein was what was called the Eddington experiment, because Einstein published his stuff in about general relativity, those papers, the Annulus Memorabilis or whatever. It was all like 1919, I think was the year. Or no, it was 1915, sorry. But then there were no experiments done to say, well, okay, you wrote a bunch of equations on paper, so what? It was the Eddington experiment, which was in 1919, which was really testing the extent of solar light deflected due to the gravitation observed during a solar eclipse. So if you have Newton's framework, you would have expected the deflection to be much less, I'm pretty sure it was, but then by general relativity, that gravitational deflection would have been magnitudes more. So the fact that it's an order of magnitude of difference, and it was this event of a solar eclipse, that is how then general relativity could be vindicated. And then further down the line, when you develop GPS, let's say, then by having general relativistic frameworks with your satellite triangulation and stuff, you can actually have a GPS measurement where it's like on the scale of size of a person and not being like miles off or something like that with your GPS triangulation, because you've narrowed down your understanding of where the Earth is and where the planets are with greater precision with general relativity. Then GPS works out. Also, developing nuclear weapons. That's also another one. But, okay, where am I going with this rant? Quantum gravity would then be somewhere in the middle of like quantum mechanics and general relativity, looking out at like, you know, celestial bodies or like high energy plasma events, stuff that's out in the galaxies, right? Because plasma is the most abundant form of matter. It's the fourth state of matter, but plasma is the most abundant in the universe overall. But we don't really think of it all the time on Earth, right? Like electrical arcs and stuff, that's like a plasma, or like metals could be understood to be plasma because the electrons are delocalized in them and stuff, right? But okay, so what I just said about there being that Eddington experiment with the solar eclipse, that vindicates general relativity. And then we have, Schrodinger's equation and all that stuff. That gets vindicated because you can do experiments and measurements, and they have that whole don't think, just calculate mantra when you're doing heavy quantum mechanics stuff, right? It's where the calculations come out perfectly, but then when you step back and you want to have the physical interpretation of those results, then you run into, problems, right? Trying to like actually explain in words like what is going on when the waveform collapses and blah, 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 right? And so quantum gravity, when you throw that phrase in, is supposed to unify those things. But with the lack of an experiment is a big problem. And then this is when it starts getting into tinfoil hat conspiracy theory land, because what would perhaps vindicate a theory of quantum gravity on the like human scale of things, so not the very, very, very small scale of quantum mechanics, not a very large or high energy plasma scenario like where we're observing these things out in the galaxy. It would be something like a time machine, or it would be something like explaining the pyramids of Giza as like a solid state energy producing device that's, the higher precision beyond general relativity of looking at like metamorphic geologic rock deposits, and you build these pyramids at the surface, and there's gold plating and blah 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 involved, that then this pyramid becomes a big power plant. But you wouldn't be able to conceive of or design that kind of structure if you didn't implicitly have like a quantum gravity like theory, or the other conspiracy theory object that you would engineer with this would be the time machine, right? So it would be like, well, you have these exotic metamaterials that are manipulating plasma fields in a way that you can get to a higher quantized level of gravitational potential, and then this field, it would kind of, the time machine that you have would be like a nuclear submarine where it's displacing itself through this gravitational potential field that you create with, right? But you can't actually go from A to Z with that without the quantum gravity theory in the middle, right? And so, but if you want to develop that, you have to really get into the weeds of the mathematics and the definitions of all of like the current state-of-the-art descriptions of general relativity, blah, blah, blah. And that's where the physicists run into problems, is because they don't actually get formally, most physicists do not get formally trained in digging through the math. They just kind of do a math speed run, and then they get back to doing the physics day in, day out. And then there are all those problems I said about academia, where like if you've got a professor who's your principal investigator and you're like, oh yeah, I want to pursue this quantum gravity theory. I've been reading about physics, and maybe there's this avenue you can go off based upon the letters that these physicists in the 1920s were writing back and forth to each other, your professor's going to look at you and be like, hell no. We only have so much grant money, and that grant money is paying your slave wage as a grad student, right? And so then you're like, shoot, you know, I only have so many years to pursue these kinds of things. And then your buddies out of undergrad who didn't go to grad school are making six-figure salaries while you're trying to, you know, pursue this passion project of a quantum gravity theory. It's not going to happen. And even then, when you do get to, let's say, like, you know, you get your PhD, postdoc, and then you get your early associate professorships, it's still not the environment where you're going to pursue something like that. Or even if you are like a full tenured professor, you could lose a lot of your reputation by even just saying what your opinion is about these kinds of things, right? Guess what? I'm a nobody. I am no one. So I can go on here on my YouTube channel and I can say whatever the I want about what I think quantum gravity is, and that's very liberating. So, wow, that was a long one, but we're finally going to get back to the reading, and I'm going to do the problems that were at the end of section 19. I will just say one of the problems that I've, not the problems to work out here, but an issue with what I'm working with here, the PDF is missing the pages in the solutions at the end. It's as if two physical pages from the book that was scanned to make this PDF are missing. And it just turns out that those are now the solutions for, it cuts off in the middle of problem 19.2 here. So I'm going to actually have to read from the book, scan it in, and you guys probably won't notice it, but I'm just saying. So problem 19.1, investigate the contact of the surface, capital S proper, which is equal to x sub 1 squared plus x sub 2 squared plus x sub 3 squared minus r squared equals 0 with the curves capital C proper, which is given by the vector parametric representation x in terms of arc length s, which is equal to, in the first dimension, s, in the second dimension, r, and in the third dimension, 0. Problem 19.1 solution. The surface is a sphere S of radius r with center capital M at the origin of the coordinate system in space. The curve is a straight line capital C in the x1, x2 plane, which is parallel to the x2 axis and lies at the distance r from that axis. If we insert the representation of C, capital C, into that of capital S, we find that P of S equal to the function capital G. Okay, remember this is going to be the representation of a surface. Capital G of x1 of S in the first dimension, x2 of S in the second dimension, and x3 of S in the third dimension. This P of S is equal to S squared plus R squared minus R squared, which is equal to 0. That is, the point P, capital P, evaluated at the arc length S equals 0 of the curve capital C is also a point of S by P of S resolving itself to 0 in the previous computation. We have dP ds, that is to say the first derivative of P in terms of arc length S, equal to 2S. And we also have d squared P ds squared, the second derivative of P in terms of arc length S, is equal to 2. Therefore, the contact of the capital C curve with capital S, the surface S, at capital P, the point corresponding to arc length S equals 0, is therefore of first order. For example, the circle x sub 1 squared plus x sub 2 squared minus r squared is equal to 0 and x3 is equal to 0, which lies on S, has contact of first order with the curve capital C at capital P, the point. All right, that wasn't so bad. This one might get a little more intense because it's where the pages get lost in PDF, but we have problem 19.2. Prove that, in general, the osculating plane is the only plane which has a contact of second order with a curve. Solution of problem 19.2. we may represent a plane of the form vector A dot product with vector Z plus the scalar D equal to 0. And that was done in a problem from the preliminaries section. Let Z the vector be equal to x naught be the point at which the curve capital C proper has a contact with the plane given by vector A dot with vector Z plus scalar D equal to 0. In order that this contact be of second order, we must have, by the definition of contact, we have first that the dot product of A with x sub 0 plus D equals 0. Secondly, we have that A dot with the first derivative of the vector Z evaluated at Z equals x sub 0 is equal to 0. And furthermore, we have that A dot with the second derivative of Z evaluated at Z equals x sub 0 is equal to 0. And this is due to the lemma which was proved in the last stream. We denote by x naught prime and x naught double prime the derivatives of the vector Z at the point x sub 0. In consequence of the first derivative and second derivative requirements of contact, which we elaborated for what we're working with, this vector A and vector Z in the line above, the vector A is orthogonal to x sub 0 prime and x sub 0 double prime. That is, if x sub 0 prime cross product with x sub 0 double prime is non-zero, and the vector A is of the form A equal to the scalar C times the cross product between x sub 0 prime and x sub 0 double prime, where C is a real number. The vectors x sub 0 prime and x sub 0 double prime span the osculating plane capital S sub 0 of the curve at the point x sub 0. Because of the A being equal to C, the real scalar, multiplied by the cross product of x sub 0 prime and x sub 0 double prime, the normal vector A of the plane under consideration is orthogonal to capital S naught. This completes the proof. Also not very bad. Okay, problem 19.3. Determine the conditions which a curve must satisfy in order that the centers of the osculating spheres be the same for all of its points. This one is not so bad either. Problem 19.3, solution. Let the vector parametric representation x of S in terms of arc length be a representation of the curve capital C under consideration, where, of course, as I just said, S is the arc length of C. In order that the centers of the osculating spheres be independent of arc length S, we must have that the first derivative of the vector A in terms of arc length is equal to the 0 vector. That is, that the first derivative of the vector A in terms of arc length is equal to x dot plus rho dot times p, which is the unit principal normal vector, not the derivative of it. So it's rho dot times the vector p, but then we have plus rho times the derivative of p in terms of S, the derivative of the unit principal normal in terms of arc length, plus d ds of the quantity rho dot over tau closed quantity, so the ratio of the derivative of the radius of curvature over torsion times the unit binormal vector b plus the derivative of the radius of curvature rho dot over torsion tau times the first derivative of the unit binormal vector b in terms of arc length, that is b dot, which is equal to the quantity rho times tau plus dds of the quantity rho dot over tau, close both quantities, times the unit binormal vector b equals 0. And this is due to the Frenet formula and the position vector of the center of the osculating sphere, which is the vector A equals the vector x, which corresponds to the point on the curve C, which the osculating sphere is being defined about, plus rho, the radius of curvature of the osculating sphere, times p, the unit principal normal, plus rho dot over tau, the first derivative of the radius of curvature in terms of arc length over torsion, times b, the vector for the unit binormal. From this, we have that the radius of curvature times torsion plus dds of the quantity rho dot over tau is equal to 0. And from the relation for the radius of curvature of the osculating sphere, we have dds of the radius of the osculating sphere squared is equal to 2 times rho dot over tau times the quantity rho times tau plus dds of the quantity rho dot over tau. That is, the radius of the osculating spheres is constant. All osculating spheres of the curve C coincide. Hence, the curve C lies on a sphere, and curves of this type are called spherical curves. So, derived straight from the definitions, and from here we can go back to reading the PDF, and we are at section 20. This is a big one. There's a big proof in here. It's an existence and uniqueness proof. And there's also one more part of it, but we're going to see what that is. Natural equations of a curve. So far, a curve capital C proper was always represented in the form given at the beginning of this chapter. X is a vector in terms of a parameter t, where the arbitrary allowable parameter t was sometimes specified by the arc length s of the curve C. And I would say most of the time we've been using arc length as that parameter, if I'm being honest. Clearly, the analytic form of such a representation depends on the choice of the coordinate system in space. Therefore, the question arises whether there is a possibility of characterizing a curve in a manner independent of the coordinates, except for the position of the curve in space. That is, to within direct congruent transformations. And now we're really seeing why I did that 7-section speed run like 4 episodes ago. We're bringing in direct congruent transformation. It's just a way of putting in these vectorized representation of curves. We want to preserve the notion of geometric congruence, where we don't want to have our definition be so strict on how we're defining the points. It's all about the relations of the point sets with each other, but we need to be able to use the big tools that we have from analysis, topology, maybe even a little bit of abstract algebra, right, in order to keep on developing what we're calling differential geometry here, right? The earliest investigation of this problem was already made more than 200 years ago by Leonhard Euler. And this guy has the most citations in the bibliography that this guy, Erwin Kreyszig, when he was writing this book, he referenced. So Euler has 6 citations in the back, which is par for the course with Euler. That's why they call him Leonhard Euler, is because he published so much math, right? Goes without saying. When trying to find such a representation, we have to look for quantities which are independent of the choice of the coordinates and parameter, but depend only on the nature of the curve, that is, on its geometric shape. The arc length s, the curvature kappa, and the torsion tau are quantities of this kind. 2 independent functional relations between s, the arc length, kappa, the curvature, and tau, the torsion, are called natural or intrinsic equations of the corresponding curve. We shall use the 2 natural equations, kappa equals kappa of s, that is to say curvature in terms of arc length, tau equal to tau of s, that is to say torsion in terms of arc length, in our further investigations. We will prove that if kappa of s and tau of s are continuous in an interval, these functions determine an arc of a curve uniquely, except for its position in space. As a consequence of this theorem, which will be proved shortly, we may state the fact that any invariant with respect to direct congruent transformations which can be associated with a curve is completely determined when the corresponding functions kappa of s and tau of s are given. The solution of our problem turns out to be very simple if kappa of s and tau of s are analytic functions, since in consequence of the formulae of Frenet, the coefficients of the Taylor series development of the function vector x of s representing the curve involve only the functions kappa of s and tau of s and their derivatives. X of s is uniquely determined when analytic functions kappa of s and tau of s are given. Returning to the general case, we have the important Theorem 20.1. Let kappa of s, which is greater than 0, that is to say we have positive curvature, and curvature is given by this function kappa in terms of arc length s, and tau of s, so correspondingly for torsion, let kappa of s and tau of s be continuous functions of a real variable s defined in an interval capital I, which is arc length s, which is less than or equal to a, but also greater than or equal to 0. So the interval I is defined by arc length, which is bounded below by 0 and bounded above by a, but it includes or is closed at those bounds of 0 and a. And I cannot reiterate enough that this is a real value s in this interval, because this is going to be an existence and uniqueness proof relying on continuity. So you're going to have to brush up on your real analysis definition of what continuity entails for a function, okay? Then there exists one and only one, so we have the existence and one and only one uniqueness, arc x of s of a curve determined up to a direct congruent transformation with arc length s, whose curvature and torsion respectively are given by the above functions kappa of s and tau of s. And now for the proof. Part 1, existence. Kappa of s and tau of s being given, the formulae of Frenet are three systems of ordinary linear differential equations in the components of the unit vectors t, p, and b, t being the tangent vector, p being the principal normal vector, b being the binormal vector, of the moving trihedron. Or if you're in Calculus 3, I've seen related videos on my moving trihedron, the previous differential geometry stream. They call these the TPB frames. We're giving it a secular phrasing there instead of moving trihedron and Frenet formulae. We just call it TPB frames, I guess, here in America. That's an aside. We have t sub I of s dot. So this is the first index of the tangent vector. It's a function, it's in terms of s, and we have the first derivative, so it's dot. I'm not sure what the best way to read that is. T dot sub I of s is equal to kappa of s times p sub I of s. Then we have p dot sub I of s is equal to negative kappa of s times t sub I of s plus tau of s times b sub I of s. And then we have b dot I sub s equal to negative tau of s times p sub I of s, where I is equal to 1, 2, or 3, and we have positive curvature. Capita is greater than but non-zero. So to reiterate, the formulae of Frenet are giving the vectors of the moving trihedron. It's a right-handed orthogonal coordinate system that you can assign to any point on a curve, and you get these vectors t, p, and b. And so the formulae of Frenet are then described in terms of each other and their derivatives. And so you could also have the skew symmetric coefficient matrix representation of these formulae of Frenet, and I believe that comes into play here shortly. So just a recap, if you feel disoriented dropping into the middle of a differential geometry math book, I'm sorry. For the sake of simplicity, we set t equal to v sub 1, p equal to v sub 2, and b equal to v sub 3. Therefore, we have written in vector form differential equations of the type v sub j dot, and I will also say that this dot notation for derivatives is confusing in its own, because the prime notation is used for just like mapping to a real line. That is what the parameter would be if they were going to use prime notation. But then when it's mapped into arc length, where we're using s, then they decide to use dot notation for the derivatives. And I think that that is a messed up mistake when you're writing a differential geometry book, given the amount of scalar products or dot products that get involved. And I think that was a real mistake on Erwin Kreyszig's part. I'm sorry. Okay, v sub j dot is equal to the sum from k equals 1 to 3 of c sub j sub k, which is a scalar, times the vector v sub k, where j is equal to 1, 2, or 3. So we're just rewriting the moving trihedron in terms of v so that the equations on the page don't get too atrocious. The reading is already probably super atrocious. We write these equations again in scalar form, omitting the index I by which the different components of the vectors v sub j are denoted. That is, we write these equations again in scalar form, omitting the index I by which the different components of the vectors v sub j are denoted. That is, we write what we previously stated was how we're going to write these formulae of Frenet moving trihedron vectors in the form v sub j dot is equal to the sum on k from 1 to 3 of the scalar c sub j sub k times v sub k, where j is equal to 1, 2, or 3, in the elements of the coefficient matrix, which we will call the entries c sub j sub k, and they're given by, like I said, this skew symmetric representation of the coefficients of the formulae of Frenet. I will say the diagonal is 0 all the way across, and I'm not going to read all 9 entries of this matrix, let's be real guys. But in the elements of this coefficient matrix, there are continuous functions in the closed interval of this domain S, which is bounded below, closed at 0, bounded above at A, closed, or z is less than or equal to s, which is less than or equal to a. That's what we're denoting by the interval capital I. And consequently, these entries, which are functions, are bounded in this interval I. Namely, the magnitude of each of these entries, c sub j sub k, is less than or equal to this arbitrary value k over 3, but k is positive, and the convenient bounding here is going to come in play momentarily, because when you're writing, if you're doing this proof, let me just say, on your own, and you figured out the idea of how to do it without reading this, let's say, and the first time you go through, you might not write k over 3, but you would have some other just arbitrary like epsilon, let's say. But then once you get to the end of doing the proof, you say, oh, you know what would make the presentation of this proof a lot more convenient? I'm going to go to that epsilon and I'm going to write k over 3, okay? So sometimes when you're reading these proofs and you run into something like that and you're like, well, how did that get pulled in here? You read to the end, and then at a second time around of thinking about how that proof went down, you'll be like, oh, that's why it was. So we have to prove that there exists a solution of this system of ordinary differential equations, which don't we love systems of ordinary differential equations? In whatever way we're going to do it, whether it's with matrices or what have you, then satisfying given initial conditions, say v sub j evaluated at 0 is equal to v sub j within a superscript 0, where j is equal to 1, 2, or 3, where we have to assume that the magnitude of these initial conditions is less than or equal to 1, since these quantities are components of unit vectors. Yeah, we have to, that's just giving you a plan of what we're going to do. The proof of existence will be carried out by means of iteration. The basic idea of this method is as follows. If there exist functions v sub j of s continuous in I and satisfying the above representation of our system of differential equations, then for all values of s in our interval I, we must have that v sub j of s is of the form initial condition v sub j superscript 0 plus the integral from 0 to s of the sum from index k equals 1 to 3 of scalar real c sub j sub k evaluated at sigma times v function sub k evaluated also at sigma d sigma must hold. So we're going to write these functions, which are going to be the approximate solutions for the differential equation systems that we have going on. It might just be me, and by the fact that I came out of a little bit of an engineering background, but the thing about if you want to apply mathematics in engineering, there are systems of differential equations all over the place. So maybe it's just because I'm numb to seeing this kind of stuff kind of brought up when we're doing things. But this is not that bad. This is not that bad. It's just saying, you know, you've got your system of differential equations, and you may say, oh my gosh, that sounds terrible. Well, really, no, it's not. It's just linear algebra dressed up as something sounding scary, but it's really not, which is, it's the scary thing being differential equations. But it's like when you realize it's all linear algebra at the end of the day, kind of, if you really think about it, it's not that bad. It's just that linear algebra, you've got ax equals b. Just imagine that x is just a bunch of derivatives. And that's what it is we're just sweeping away the derivatives into a vector so that you can really focus on what's going on in that matrix, right? So like saying, oh, it's a skew symmetric matrix. That makes things a whole lot easier, right? And then, if we're solving these differential equations, right? If you're doing it like the trivia bowl style, right? You would expect that you get like this, you're given this function and it's, crazy polynomial over another polynomial with all these logarithms in there. And then you're expected to get this exact symbolic representation output. Guess what? That is like never how it goes down in quote unquote real life. Thank goodness. You just need basically one method, and that's a good way to have an approximation, okay? So when you're given this system of ordinary differential equations, all you need is a good way of writing what a general like approximate solution would be. Taylor series out, cut off as many terms as you need to be precise in your application, you're good to go, right? That's basically all it is. Replacing the functions v sub k in the integrand of this approximate function solution we just spelled out here, then by the initial values of v sub k superscript 0, we obtain 3 first approximate functions. We need approximations for all the derivatives that we're going to be using. That's what these are. So the first derivative of v sub j is equal to the initial condition v sub j superscript 0 plus the integral from 0 to s of the sum on the index k from 1 to 3 of scalar quantity c sub j sub k times v sub k superscript 0. Then you obtain these approximate functions. So if we first insert three first approximate functions, v sub j first derivative, into the integrand of the 0th order approximate function, I guess you could say, we obtain three second approximate functions, which are the second derivatives of v sub j, etc. By inserting the n minus 1th approximate functions v sub k n minus 1 derivative, we obtain three nth approximate functions, which are the nth derivative of v sub j is equal to the initial condition v sub j superscript 0 plus the integral from 0 to s of the sum on the index k from 1 to 3 of the scalar c sub j sub k times v sub k n minus 1 derivative d sigma, where j is equal to 1, 2, or 3. We have to prove that when n increases arbitrarily, then the nth derivative of v sub j tends to a limit function satisfying the initial condition. Since the magnitude of our initial condition v sub j superscript 0 is less than or equal to 1, we obtain from the statement of the boundedness of the magnitude of elements of the Frenet formula's coefficient matrix, again, that's the magnitude of c sub j sub k is less than or equal to k over 3, where k is positive, and from the equations previously derived for the first approximate function for the solutions of the system of ordinary differential equations, where we have the vector v sub j first derivative is equal to the initial condition v sub j superscript 0 plus the integral from 0 to s, etc. From those things, we get that the magnitude of the difference between the, I guess you could call it the first derivative approximate solution minus the just initial condition for the solution overall, v sub j superscript 0, the magnitude of that is less than or equal to k times arc length s. So this is the point where it might come full circle that the value of the boundedness of the magnitude of the elements of that Frenet formula coefficient matrix, the value that it's bounded by was k over 3. Now we see why. Because it would kind of be inconvenient moving forward to have 3 times epsilon when we computed this magnitude here, filling in the blanks, which I'm not going to do. Similarly, the magnitude of the difference between the second derivative approximate solution and the first derivative approximate solution is less than or equal to k squared times s squared over 2, and in general, the difference between the nth of your approximate solution for derivatives and your approximate solution for your n minus 1th derivative, that is less than or equal to k to the n power times s to the n power over n factorial. So with that, now we have that the approximate solution for the nth derivative of v sub j is equal to the initial condition for the overall solution, so v sub j superscript 0, plus the difference between the first derivative minus the overall initial condition, but then that's plus a similar term where we have the second derivative approximate solution minus the first derivative approximate solution. So you can figure that there's going to be a lot of cancellation going on. So in this representation, the absolute value of each term is at most equal to the corresponding term of the sum. Overall approximate solution initial condition v sub j superscript 0 plus k times s plus k squared times s squared over 2 factorial plus etc. plus k to the nth power times s to the nth power over n factorial. If n tends to infinity, then this expression tends to the initial condition for the approximate solution overall, v sub j superscript 0 minus 1 plus e to the k to the s. Wow. We just got a implicit derivation of the Taylor series expansion for the exponential function, where the value is that bound on our elements of the Frenet formulas times arc length s. So we have our initial condition, v sub j superscript 0 minus 1 plus e to the ks. Wow. Hence the series v sub j superscript 0 plus, and then we have the difference of all those terms, converges uniformly in I, and the limit as n approaches infinity of v sub j of the nth derivative equals v sub j. Wow, incredible. The approximate functions v sub j n times derived are differentiable with respect to arc length s in our interval I, and that's according to the equations previously derived for the nth approximate functions for the solutions of our overall system of ordinary differential equations, and therefore are also continuous. Wow. This means that according to the series expansion that we have here, v sub j is represented by a uniformly convergent series of continuous functions and is therefore continuous. Wow, that's quite a way of showing continuity. So, this expression for our solution, if you will, is equivalent to v sub j plus the difference between the nth derivative of v sub j minus v sub j, which is equal to our initial condition v sub j superscript 0 plus the integral from 0 to s of the sum from the index k from 1 to 3 of scalar c sub j sub k times function v sub k d sigma plus the integral from 0 to s of the sum on the index k from 1 to 3 of the coefficient c sub j sub k times the quantity n minus 1th derivative of v sub k minus v sub k d sigma. If n increases arbitrarily, then for all values of s in our interval I, the function's magnitude of the difference between the nth derivative of v sub j minus v sub j and the magnitude of the difference between the n minus 1th derivative of v sub k and v sub k, the difference, n minus 1th derivative of v sub k minus v sub k, tend uniformly to 0. Therefore, we obtain from what we just determined our solutions are equivalent to, we obtain what we have determined the nth approximate derivative solutions to be equivalent to, that we've been churning out their representation to know that they are of the form of. We obtain thus that v sub j is equal to the initial condition v sub j superscript 0 plus the integral from 0 to s of the sum on the index k from 1 to 3 of c sub j sub k times the function v sub k d sigma, and from this that v sub j dot is equal to the sum from the index k equals 1 to 3 of c sub j sub k times the function v sub k. Furthermore, v sub j evaluated at 0 is equal to v sub j superscript 0. That is, the three continuous limit functions v sub j are differentiable and satisfy the formulae of Frenet and also the given initial conditions. So that concludes the first part, which is the proof of the existence of the solution and that it's continuous, etc. Now to the second part, which is the uniqueness of the solutions. We said, recall, that there is one and only one arc x of s of a curve. So we just show that there is the arc of the curve, it exists, but now that there's one and only one, this is the uniqueness component of the solution. We will now prove that there exists only one arc capital C of a curve, except for its position in space corresponding to the above natural equations. In this part of the proof, we're just going to continue using the notation where we denote the tangent, principal normal, and binormal vectors by v1, v2, and v3 for the sake of keeping all of these equations and their derivatives straight. We consider the above solution v sub j and v sub j evaluated at 0 equal to v sub j superscript 0, where j is equal to 1, 2, or 3 of the given differential equations, and the second solution v sub j star, where j is equal to 1, 2, or 3, which satisfies the initial conditions v sub j star at 0 equals v sub j star superscript 0. There exists one and only one displacement which carries these initial conditions into the others. We now let the curve defined by v sub j star undergo this displacement. Then v sub j star evaluated at 0 equals v sub j evaluated at 0. We have to prove that v sub j star of s is equal to v sub j of s for all values of s in our interval capital I. We will first give the proof for all values of s in the subinterval I tilde of I, defined by s less than or equal to 3 over denominator 2 times k. Again, this is probably going to be another constant that is going to simplify itself in a later part of the proof. So if you're thinking again, why is it that s is bounded by this 3 over 2k? Let v sub 1, v sub 2, and v sub 3 denote corresponding components of vector v1, vector v2, and vector v3. Let s sub j be that value of s in I tilde for which the magnitude of the difference between v sub j star and v sub j, so the magnitude of v sub j star minus v sub j, assumes its maximum value, say capital M sub j, in consequence of the formulations for the approximate solutions of the system of ordinary differential equations defined by this endeavor, you could say. We find that capital M sub 1 is equal to the magnitude of the difference between v sub 1 at s1 and v sub 1 star at s1, or v sub 1 at s1 minus v sub 1 star at s1, which is equal to the magnitude of the integral from 0 to s sub 1 of v1 dot minus v1 star dot. So we have the first derivative in terms of arc length of the function v1 minus the first derivative in terms of arc length of the function v1 star is equal to the magnitude of the integral from 0 to s1 of the coefficient kappa representing curvature times v2 minus v2 star ds, which is less than or equal to k times capital M sub 2 all over the denominator 2k. Hence, capital M1 is less than or equal to 1/2 capital M2. Using the second and third formula of Frenet, we similarly find that M2 is less than or equal to 1/2 quantity sum of capital M and M2, and that capital M3 is less than or equal to 1/2 capital M2. Adding these three inequalities, we have capital M1 plus capital M3 is less than or equal to 1/2 times the quantity capital M1 plus capital M3. Since, by definition, capital M sub j is greater than or equal to 0, we thus have capital M sub j equals 0 for j equal to 1, 2, or 3. This means that for all values s in I tilde, the subinterval of I, the relations v sub j star of s equal to v sub j of s hold. Repeating this argument, we obtain that v sub j star of s equals v sub j of s for all values of s in I. This completes the proof of uniqueness. Going on to the third part here, we will now prove that if the vectors v sub 1 superscript 0, v sub 2 superscript 0, v sub 3 superscript 0, form an orthonormal system for any value of s, namely s is greater than or equal to 0 and s is also less than or equal to a. The vectors v sub j of s are equal to, in the first dimension, v sub j1 of s, in the second dimension, v sub j2 of s, and in the third dimension, v sub j3 of s, where j is equal to 1, 2, or 3, also forms such a system. That is, we have to prove that the matrix column vector of vectors v1, v2, v3 is equivalent to 3 by 3 matrix expanded out. I'm not going to read it. Is orthogonal for any value of s where s is greater than or equal to 0 and less than or equal to a, if it is orthogonal for s equals 0. It suffices to prove that the column vectors of this matrix satisfy the relations sum from 1 to 3 on the index I of v sub I sub alpha of s times v sub I sub beta of s is equal to delta sub alpha beta, where alpha and beta are 1, 2, or 3, since the row vectors then satisfy the analogous relations as is well known. If the derivative with respect to s of the sum that was just described vanishes, then this sum is constant and for reasons of continuity equal to its value delta sub alpha sub beta at s equals 0. In consequence of the formulae of Frenet, v sub j sub I dot equals the sum from 1 to 3 on the index k of c sub j sub k times v sub k sub I. We have d ds, or the derivative with respect to arc length, of the sum from 1 to 3 on the index I of v sub I sub alpha times v sub I sub beta is equal to the sum from 1 to 3 on the index I of v sub I sub alpha dot, which is the first derivative of v sub I sub alpha in terms of arc length, times v sub I sub beta, plus v sub I sub alpha times the derivative of v sub I sub beta with respect to arc length, which is equal to a sum of sums where the outer sum from 1 to 3 on the index I is of the inner sum from 1 to 3 on the index k of c sub I sub k times v sub k sub alpha times v sub I sub beta plus v sub I sub alpha times c sub I sub k times v sub k sub beta, or when interchanging I and k in the second term of each summand, the derivative with respect to s dds of the sum from 1 to 3 on the index I of v sub I sub alpha times v sub I sub beta is equal to the sum of sums with the outer sum from 1 to 3 on the index I of the inner sum from 1 to 3 of the index k of quantity c sub I sub k plus c sub k sub I closed quantity times v sub k sub alpha times v sub I sub beta. Since c sub I sub k is equal to negative c sub k sub I, this expression vanishes. The determinant of an orthogonal matrix has the constant values plus or minus 1, depending on the orientation of its row or column vectors. For reasons of continuity, the orientation of the vectors v sub 1 of s, v sub 2 of s, and v sub 3 of s is the same as that of the given vectors v sub 1 superscript 0, v sub 2 superscript 0, and v sub 3 superscript 0. Hence, we conclude that if the given vectors v sub 1 superscript 0, v sub 2 superscript 0, and v sub 3 superscript 0 form a right-handed orthonormal system, then the vectors v sub 1 of s, v sub 2 of s, and v sub 3 of s on s is greater than or equal to 0 and less than or equal to a are uniquely determined and also form such a system. The representation of the corresponding arc can be obtained by integration, namely, the vector parametric representation x of s is equal to x sub 0, where x is a vector, plus the integral from 0 to s of the function t of sigma d sigma, where s is greater than or equal to 0 and less than or equal to a, where x sub 0 denotes a constant vector. The initial conditions can differ in x sub 0 and the direction of the trihedron T superscript 0, P superscript 0, and B superscript 0. There's exactly one direct congruent transformation which transforms a certain initial condition into another given one. The given functions kappa of s and tau of s for curvature and torsion remain unaffected by this transformation. Hence, in consequence of the uniqueness of the solution, any two solutions corresponding to different initial conditions become identical under a suitable direct congruent transformation. Okay, before I read the next section, I'm going to continue the rant a little bit that I started in the introduction, because on second thought there were a lot of things that I wanted to say that I did not. So to make things easier again, I'm going to draw a picture, and well, not a picture, this one's going to be like writing stuff down in a table perhaps. So let's say we have three different regimes of what we're interested in physics as human beings, I guess. So we have the very large, and this could be things like celestial bodies, right? Planets that we see in the sky and things of that nature. It could also mean asking questions that involve things that are very large, such as what if you have a spaceship that either orbits the sun for 1,000,000 years, or it goes out almost at escape velocity away from the sun and back, knowing that by the time it comes back, by the time it falls back to the sun, it will have been gone and back over 1,000,000 years. So I would say those things are on the scale of very large. You could also say very large in terms of like high energy, so toss in everything about plasma in there. But then you have also the very small, and so this would be everywhere that quantum theory applies. And like I said, the standard model of particle physics. So that is all very small. And then we have in human scale, let's just call it. And Newton's ballistic, his interpretation of gravity is good enough for all of that. And we have in here Maxwell's equations, of course. But with these alone, that accounts for like 99% of our technology. And so you're like, well, why would we need anything else? Well, it's kind of like how there was that experiment about the measuring the gravitational deflection of light during the solar eclipse that Einstein proposed in order to vindicate his theory of general relativity. Okay, so that experiment I would put on the border of very large and human scale, because the magnitude of the difference between Newton's model, what it would have predicted the light deflection to be, and what Einstein's theory predicted to be, it's on a human measurable scale. Nevertheless, the results can be applied to things that are very large, right? Like GPS is on arguably a fairly large scale, or applying that to astronomical observations and stuff. But one of the problems then on the very small side is that notion of observability, right? And it's things like Schrodinger's cat and the trade-off between your uncertainty in measuring momentum and your uncertainty in measuring position, and how that seems like a fundamental trade-off in physics as we understand it. All of that is contingent on an unspoken understanding of what an observer is. And if you start to get any deeper into that, you ultimately just question what is consciousness. And so it brings what is the so-called hard problem of consciousness into the mix, which I would state simply as if the soft problem of consciousness is saying that we are this emergent property of the billiard ball's representation of the universe and reality. That's all that consciousness is just kind of how a song is. If you have like a record player, the sound experience, perception that's played from the record player with the record, etc. Consciousness is just analogous to that song, but then our human bodies and this material existence and stuff like that is just the emphasis on the vinyl record, the record player, etc. But the hard problem of consciousness is then going the other way around, which is asking like, why are there the qualities that we associate with consciousness, or why is it that there are then in our day-to-day experience we intuitively feel that there is this immediacy to our experience and stuff like that, which no one would say that consciousness does not exist in themselves or in other people very seriously, I guess. So that's what the hard problem of consciousness would be. And so that, I would argue, is kind of on the border between the human scale and the very small scale, because the soft problem of consciousness involves things like, the biological components that make up brains and stuff, the different tissues and specialized cells and the signaling that happens and blah, 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 right? But then that's part of the problem, is that what in the middle would be added by quantum gravity, like you could say UFOs, yeah, freaking pyramid power here. We can't actually build those things right now. Or like, who in Egypt would allow a group of engineers to come in and say, hey, if we made these modifications to the Great Pyramids, we think that it would start working like a power plant? No one would okay that in 2024, probably in like a few decades, at least, I imagine. So it's like, why would you need to go beyond our own understanding of gravity? Well, that's the thing. We lack an experiment that would go all the way across all these things. If you're talking about consciousness, what kind of an experiment could you run that does not involve the risk of killing whatever houses or contains that consciousness, right? Unless you are 100% certain already in your operational model of consciousness, then there's inherently going to be a risk of death. Conversely, though, if you were thinking of maybe taking lab rats or whatever and trying to raise consciousness in them, then it's like, well, even if you do succeed in them, that still seems like an unethical thing to do. Like attributing what we would say is human consciousness to like a lab animal, once you do it successfully, like you're still gonna want to euthanize that terrible creature, I guess, because like what kind of an existence is that? You know what I mean? Like that doesn't really sit very well with people. But if you were to ask me right now if I could describe what it was in math only, if you were on your way to getting that actually correct, how would you describe consciousness from a quantum mechanical perspective, and then hope that you have this other quantum gravity theory that you could collapse the equations down into and it all unifies in the middle, where we're like, hey, if you're on Earth and you have two objects of different masses, their rates of speed increase as they fall is going to be the same, right? So this is what I would say. Start off with the polar wave equation. And so that is psi, psi of r and t. So we have a space dimension, we have a time dimension for our wave. We're describing in polar coordinates, which is equal to r of rt times exponential function I s r t all over h bar, where r and s are the physically real fields describing the time evolution of the energy constituting the particle that's being described by this polar wave equation. Before I go any further, I would also like to say that the wave equation was philosophically the result of, well, the actual result is by this guy named Jean d'Alembert, a French guy, but philosophically he was anticipating essentially the transcendental idealism which would later come about by Immanuel Kant. He did not believe that there was anything in existence unless there were human minds in the first place. So it's to say there is no hard reality without human consciousness, spirit, or otherwise. D'Alembert was after that, in that he started to doubt whether there was anything material if there were not human consciousness, but it opens the door for then later there to be someone like Immanuel Kant to come in with transcendental idealism. But as we all know, Immanuel Kant is a member of philosophical trajectory, so Kant is contended with by people like Hegel, with Hegel, of course, having brought to bear absolute idealism, and some people say that that's the end of philosophy. Unless, you know, another German after Hegel, you're like Heidegger, and you think this entire progress that we've made after Socrates, after the triple trifecta powerhouse of Plato, Socrates, and Aristotle, Heidegger thought that it was all downhill from there, that we've only gotten worse. Heidegger, with his work in metaphysics, is basically confronting Descartes and saying that Descartes is part of the problem, and he helped steer Western civilization's philosophy down a dead end. And so Heidegger was saying that we need to go back to the pre-Socratic times. Or you could go with Hegel from the late 1800s and say absolute idealism is the way to go. We can go beyond Kant. Okay, but this guy, D'Alembert, who came up with the wave equation, was philosophically anticipating Kant, essentially. And that is where I would kick this off. So we have the polar wave equation, and I would substitute this into the Schrodinger equation, partial s partial t plus 1 over 2m del s squared plus v. Also, this is after I inserted the polar wave equation into the Schrodinger's equation, separated off the imaginary part, kept the real part. This is what I got. And this is just a statement of conservation of energy. At this point, you could do what's called, I guess, from my limited understanding, what's called a WKB approximation, where this Q term goes to 0. And what you're left with is classical mechanics. So basically it's kind of, this is what I mean when I colloquially say, oh, you have your non-human scale model of physics. In this case, it's the quantum theory of physics, Schrodinger's equation, right? And you can use Schrodinger's equation to get these, don't think, just calculate great results at the very small scale, but you can also mathematically manipulate the equations here, literally Schrodinger's equation, and what you get out from that when you bring it back in a way to the human scale is you get classical mechanics still. But if you don't do that WKB approximation, this Q right here could be this field of so-called active information. Yeah, a field or a potential of active information is what this term could be. And qualifying that further could probably be what consciousness is as we think of it and stuff. But it's kind of like I said, then so what? Because there are so many theories out there that are just like what I just said, quite poorly, honestly. But there's a lot of theories out there that are like that, except the problem is the experiment that you would need to do in order to prove that. Even if you did come up with it, it would be very frowned upon in the West or in like normal university academia and stuff. So I had just been reading from section 20, which described or just did a proof of the existence, uniqueness of the natural equations, and it's all just to say that the curvature and torsion are a way to specify a curve independent of whatever coordinate system you're representing it in. So the parameters that you choose in Euler's vector parametric representations, it is all contingent upon what coordinate system you choose, and the entire proof that section 20 is just vindicating that curvature and torsion, it's all good. That's a way to represent your curves, and you don't have to worry about the coordinate system that you choose. That's the takeaway that I got from that. Anyways, section 21 are now just examples of curves and their natural equations. In addition to the preceding section, we will now consider some examples of curves and their natural equations. We will at first point out the following fact concerning plane curves. If alpha of s denotes the directed angle from the positive ray of the x1 axis to the unit tangent vector t of s to a plane curve capital C, then alpha of s is continuous, and the vector t is equal to, in the first entry, cosine of alpha, and the second entry, sine of alpha, and d alpha of this vector t is equal to, in the first entry, negative sine alpha, and in the second entry, cosine alpha. And d alpha of t dotted with the vector t, or the scalar product of d alpha of t with the vector t, is equal to 0. The unit vector d alpha of the vector t is therefore orthogonal to the vector t. That is, d alpha of t is equal to plus or minus the vector p. Now, from the formulae of Frenet, t dot is equal to d alpha of t times d alpha ds, which is equal to kappa times the vector p, or curvature times the unit principal normal vector. Therefore, since curvature is greater than or equal to 0, by comparison, curvature is equal to the magnitude of d alpha ds. On an arc of C, on which kappa is non-zero, then choosing the suitable orientation, we finally obtain kappa is equal to d alpha ds. First example, the natural equations rho equals r equals constant and tau is equal to 0 yield a circle of radius r. And indeed, using kappa equal to d alpha ds, we have that dx d1 is equal to ds cosine alpha, which is equal to r cosine alpha d alpha, and dx2 is equal to ds sine alpha, which is equal to r sine alpha d alpha. And therefore, x1 is equal to r times the integral from 0 to alpha of cosine of phi d phi equals r sine alpha, and x2 is equal to r times the integral from 0 to alpha of sine of phi d phi equals r times the quantity 1 minus cosine alpha, or x1 squared plus the quantity x2 minus r squared is equal to r squared. Okay, so second example. From the natural equations, s times rho is equal to c squared and tau equal to 0, where c is non-zero. We obtain a plane curve which is known as spiral of Cornu, and we have a picture of it on the following page. By means of kappa equals d alpha ds, we find that alpha is equal to the integral on s of d sigma over rho is equal to 1 over c squared times the integral from 0 to s of sigma d sigma equals s squared over the denominator 2c squared. And since dx1 equals ds cosine alpha and dx2 equals ds sine alpha, therefore x1 equals the integral from 0 to s of cosine alpha times sigma d sigma, which is equal to the integral from 0 to s of cosine of sigma squared over the denominator 2c squared d sigma, which is equal to c over the square root of 2 times the integral from 0 to phi of cosine alpha over the square root of alpha d alpha, and x2 equals the integral from 0 to s of sine of alpha times sigma d sigma equals the integral from 0 to s of sine of sigma squared over 2c squared d sigma equals c over square root of 2 times the integral from 0 to phi of sine alpha over the square root of alpha d alpha. Interestingly enough, these integrals are called the Fresnel integrals. They were first considered by Augustin Jean Fresnel, who lived 1788 to 1827, in connection with refraction problems, which, as I said in the last video, this guy and Cauchy both led science up to that critical mass for Maxwell to then swoop in and connect light with electromagnetic waves, bringing us one step closer to the dual particle wave understanding of light that we're stuck with today. So thank you, Fresnel. They cannot be evaluated in terms of elementary functions. And for the tables, we can see Jahnke and MD tables of functions, New York, 1945. Since the integral from 0 to infinity of the cosine of alpha over the square root of alpha d alpha equals the integral from 0 to infinity of the sine of alpha over the square root of alpha d alpha equals the square root of the quantity pi over 2, the coordinates of the quote-unquote limit points of the spiral are x1 equals x2 equals plus or minus c over 2 times the square root of pi, as is shown in the figure of the depiction of the spiral of Cornu. And the author of the book has a shameless plug of themselves right here. For further details, see Kreyszig, his own publications. Humble brag. Third example, the natural equations kappa equals kappa of s and tau equals tau of s of spherical curves with tau being non-zero torsion must be so that the relation rho times tau plus dds of the quantity rho dot over tau, closed quantity, is equal to 0, is satisfied. And that was shown in the problem 19.3, which I did at the beginning, or read at the beginning, rather. Fourth example, an important case of plane curves are the cycloids. We first consider the ordinary epicycloid. Let capital K naught be a fixed circle of radius r naught, and let capital K be a circle of radius r, which lies in the same plane and has a contact of first order with capital K naught at a point. Capital K is assumed to lie exterior to capital K naught and vice versa. Now, when K rolls on K naught without sliding, a fixed point P of K generates a plane curve which is known as an ordinary epicycloid, as shown in figure 25 above. We denote M naught and M the respective centers of K naught and K. If the segment M naught M, starting from the positive ray of the x1 axis, has rotated through an angle of alpha, as shown in figure 25, then the angle between M naught M and MP is beta, which is equal to alpha times r naught over r. MP makes therefore the angle alpha plus beta, which is equal to the quantity r naught over r plus 1 closed quantity times alpha with the x1 axis. We can thus represent the ordinary epicycloid in the form x1 equal to the quantity r naught plus r closed quantity times cosine of alpha minus r times the cosine of r naught plus r over the denominator r times alpha. x2 correspondingly is equal to the quantity r naught plus r times sine alpha minus r times the sine of. In the numerator, we could have the quantity r naught plus r closed quantity times alpha, and in the denominator, r. This curve has the arc length s equals a times cosine of r naught over 2r and then times alpha, and a equals 4 times r over r naught times the quantity r naught plus r, where the point s equals 0 is chosen so that it corresponds to alpha equals r over r naught times pi. The radius of curvature is rho equal to b times sine of r naught over 2r times alpha, and b equals 4r over r naught plus 2r times the quantity r naught plus r. Hence, the natural equations of the epicycloid are s squared over a squared plus rho squared over b squared equals 1 and tau equals 0, where a is greater than b. Now we consider the ordinary hypocycloid, which is shown in figure 26, which is generated by the above point P when K is rolling on K naught in the same manner as before, but lies inside K naught. This curve can therefore be represented in the form x1 equals quantity r naught minus r times cosine of alpha plus r times cosine of r naught minus r over r times alpha, and x2 equals the quantity r naught minus r times sine alpha minus r times the sine of r naught minus r over r times alpha. If r naught tends to infinity, then a and b tend to 4r, and the natural equation of what we had just expressed is then of the form s squared plus rho squared equals 16r squared. The corresponding curve is called an ordinary cycloid, as shown in figure 27. It is generated by a point P of K if K rolls along a straight line. Cycloids are important in connection with technical problems, for example, in the theory of cogwheels. The earliest investigation of a special cycloid is due to the famous painter Albrecht-Dürer. Problem 21.1. Prove that all plane curves having the natural equation rho equals a times s plus b, where a is non-zero, are logarithmic spirals. The solution to problem 21.1. From the given equation, we find s equals rho over alpha minus b over alpha. Therefore, in consequence of kappa equals d alpha ds, we have that alpha equals the integral from s naught to s of ds over rho of s, or we could have the integral from s naught to s of 1 over rho of s ds, which could be rewritten as the integral from rho naught to rho of 1 over rho times ds over d rho, which equals 1 over alpha times the log of rho over rho naught, or rho equals rho naught times e to the a alpha. Also from kappa equals d alpha ds, we have that rho equals ds over d alpha, since the radius of curvature is the reciprocal of curvature, where curvature is kappa and the radius of curvature is rho. Therefore, we have the following changes of variables for the infinitesimals. dx1 equals ds cosine alpha, which is equal to rho times cosine alpha d alpha, which is equal to rho naught times e to the a alpha times cosine alpha d alpha, and dx2 equals rho naught times e to the a alpha times sine alpha d alpha. Consequently, dx1 plus ix2, so now we're going to take the infinitesimal, we're going to go to the complex plane because, we've got exponentials here. Like I said before, exponential is essential to doing complex variables work. D of x1 plus ix2 is equal to rho naught times e to the quantity a plus I times alpha d alpha, and therefore by integration, x1 plus ix2 equals rho naught times e to the quantity a plus I alpha over a plus I. I believe that's so we have a coefficient, if you will, of rho naught over denominator a plus I, and then that is times e to the quantity a plus I closed quantity alpha. From this, r squared equals x1 squared plus x2 squared equals quantity x1 plus ix2 closed quantity times quantity x1 minus ix2 closed quantity, which is equal then to rho naught squared times 1 over, I want to say, a plus I times a minus I times e to the 2a alpha. Or r of alpha is equal to rho naught times 1 over the square root of the quantity a squared plus 1, then times e to the a alpha. And this is a logarithmic spiral. Problem 21.2, and we're going to leave it there and pick it up in the next one. So, problem 21.2, determine the natural equations of the catenary x2 over c minus hyperbolic cosine of x1 over c equals 0 and x3 equals 0, as was done in problem 9.2, which is in the arc length section. So this one's nice and easy. Solution of problem 21.2, we set x1 equal to t. Then x2 equals c times the hyperbolic cosine of t over c, and the derivative of this vector x not in terms of arc length. So we have x prime is equal to, in the first entry, 1, in the second entry, hyperbolic sine of t over c, and the third entry, 0. X double prime correspondingly is 0 and 1 over c times the hyperbolic cosine of t over c, and then we have 0. So we have x prime dot x prime equals 1 plus the square of the hyperbolic sine of t over c, which equals the square of the hyperbolic cosine of t over c. We have a nice trig identity transformation there. And x double prime dot x double prime is equal to 1 over c squared times the square of the hyperbolic cosine of t over c. Thus, we have that s equals c times hyperbolic sine of t over c. S prime is the hyperbolic cosine of t over c, and s double prime is 1 over c times the hyperbolic cosine of t over c. And so from this and the equation for curvature in terms of the first and second derivatives of the vector parametric representation of a curve not in terms of arc length, so not in terms of s, but in terms of t, if that means anything in short. Due to that, it follows that rho equals c times the square of the hyperbolic cosine of t over c, or rho is equal to s squared over c plus c, and tau is equal to 0. Thus concludes a quite long-winded stream about the natural equation representation of curves. A lot of curvature and torsion all over the place. We did an existence and uniqueness proof. We went over some examples, did some problems, did some proofs. See you guys in the next one.